Hello, this is Miss Townsend. Welcome to Math with Townsend. So we've been looking at the grade 9 academic analytic geometry summative, and there's a little bit more that I could talk about regarding question 13. Now, nothing I'm about to talk about is stuff you absolutely have to know, but probably some of you are finding that the 13 questions make a lot of sense. You've followed everything that we've talked about, and you want to know a little bit more. You want to extend your knowledge, and maybe you're going into enriched grade 10, so you want a bit more information. So that's what this is. It's a wee bit more about question 13. But again, if you're kind of still not 100% sure about some of these questions, then don't worry about this video. Just, watch the other ones. So again, this was what question 13 was. It was the one about Kenji and Yvette, and they both left from the same spot, but Yvette left half an hour later, etc. So you should recall from that other video, the original question 13 video, that we at some point answered the question by saying that this point of intersection right here was when Yvette caught up to Kenji, and that it occurred at the 2-hour and 18-minute mark. And you'll remember that, how did we get 18 minutes? Well, we had five boxes on the grid represented half an hour, and that point was 3 boxes in. So we did 3 out of 5 boxes, where 5 boxes represented 30 minutes. We did the math, that was 18 minutes. So 2 things we could have done instead. So instead of saying that our answer was 2 hours and 18 minutes, we could have turned our answer into a decimal. So remember how we decided that t equals 0 was the starting value for this particular question, and that Yvette started therefore at t equals 0.5. Well, since we were using decimal time anyway, then maybe we should have answered this question using decimal time. So that's a pretty simple thing to do. 18 out of 60 minutes is what decimal portion of an hour? So I could get a calculator, but what the heck. I'm going to divide top and bottom by 6. That gives me 3 out of 10. So that means that 2 hours and 18 minutes is actually 2.3 hours. So that's one thing you could have done differently. Certainly, there's absolutely nothing wrong in my books with saying 2 hours and 18 minutes. But t equals 2.3 hours is, I guess, slightly more mathematical. So there you go. Now, there's something else I wanted to mention about that. Let me get a new page in here. And that is that maybe we answer entirely differently. So far we could say that it's the 2-hour 18-minute mark. We could say it's the where did it go? We could say that it's the 2.3 minute mark. Eraser, erase. Okay, so we could say that it's the 2-hour and 18-minute mark. That was fine. We could say that it's 2.3 hours after the starting time. But if you remember, the starting time was 1:30. So maybe we should take our mathematical answer and turn it back into clock reference, because the original question was a clock reference question. So maybe that's the best idea. So 2 hours and 18 minutes later would be, well, 2 hours later would be 3:30. Oops, that's a 3:30. And then 18 minutes more would be 3:48. So maybe we should have answered it this way. Maybe we should have said that Yvette caught up at 3:48, because generally it is a good idea to give an answer in the same format that the question was asked. And again, since the question was given in time reference, so clock referenced time, then maybe the best thing we should have done is answered with clock reference time. Again, you guys are in grade 9. perfectly fine. Wonderful answer. Hey, that deserves a smiley face for sure. That's one of the things I wanted to talk about. The other thing I wanted to talk about is going to get a little more complex. So, again, don't let this confuse you. What I'm about to talk about is nothing you have to know to do the summative. In fact, what I'm about to talk about isn't anything you have to know until grade 11. But it's interesting and it's not too challenging, I think. And it's another way of thinking about finding Yvette's equation. So you'll remember that in the original question 13, what we did to find Yvette's equation was we theoretically extended her line backwards in time, if you will, to find out what her theoretical starting value would be. So we knew she actually started here, and we knew that her line had a slope of 100 kilometers per hour. So we knew everything about her line except for the starting value. So all we did was we continued to draw a straight line until we got a starting value of negative 50. Hopefully you understood that because it sure makes sense. But I want to show you another way of doing it, which is maybe less graphical, although you know me, I always am going to draw graphs. So let's think about Yvette. Yvette really only gets interesting when t equals 0.5. That's when she's at the 0 kilometer marking. 1 hour, she's gone half of her speed. And again, her speed is 100 kilometers per hour. So a half hour, she's gone 50 kilometers. Another half hour, oops. Boy, my pen is not having a good Sunday evening. Remember, this is just the bonus app, so no refunds, no exchanges. Okay, so at 1.5 hours after t equals 0, she's gone 100 kilometers, and so on. So you can clearly tell that this is a linear relationship. So we know that this is, oh, I wanted red. We know that this is plus 50, and this is plus 50, and this is plus, red please. This is plus 0.5, and this is plus 0.5. And so to find the equation, you didn't have to use the graph at all. You certainly could have just said that d equals 100t because 50 over 0.5 is 100, plus b, and then taken any of these points and sub them in. That would have worked perfectly fine. You would have still got negative 50 as her starting value. What else could you have done? Well, if you're looking at the table of values, you could have kind of done this extending the table of values backwards trick, where I subtract half an hour. So I subtract 50 kilometers, and there's another option. So now that's another way of knowing her starting value is negative 50. All of those are great, but now comes the really, really enriched part, which is I'm going to look at this graph. Now, we know that this graph, and again, I'm only looking at Yvette. Kenji was no problem. It starts here at half an hour. The slope is 100 kilometers per hour. Now, if that graph had been here, that would have been a lot easier, right? We wouldn't have any issues really, because then we know that Yvette's equation would have been just simply 100t because she started right here. So one thing we could do, which is slightly different from the other things we've shown you, is we could say, where is Yvette at time equals 0.5? And you could say, well, Yvette at time 0.5 is here at time equals 0. Does that make sense? Let's kind of create a little chart. So this is Yvette's real, and this is Yvette's fake. Time, distance. So Yvette's real time at 0.5 is the same as her fake time at 0. That's the dotted line. Real time at 1 is the dotted line at 0.5. Real time at 1.5 is the dotted line at 100. So again, the dotted line is just an easier line to work with, right? So the dotted line is much easier to work with, and there's a relationship between the dotted line, which I'm calling fake, probably could have picked a better name, but that's the dotted line, and the real line, which is the solid line, which is if I take her real time and I subtract half an hour, then I can use this fake line. Again, take her real time, subtract half an hour, and I can use this fake line. Take her real time, subtract half an hour, and I can use this fake line. So this fake line, which is easy to understand, I can use it if I subtract a half hour from time. So do you see what I mean? Her real time at 0.5 was her real distance of 0. So if I wanted to use this equation, I could say, well, take her time, subtract half an hour, and you'll figure out where she is using this equation. And that gives us this. Now, again, I'm taking you into grade 11 territory. So if you're already lost, don't sweat it. This is the equation of this solid line. What it is it's called a transformation line. So what we did was we took this line, this easy to use, straightforward dotted line, and we transformed it by half an hour to create our real line. Now, again, don't worry if it doesn't make sense. It will in grade 11, I hope. But I just want to show you, if you're still with me and you haven't shut this off thinking I'm not ready, watch what happens. If I expand that 100 multiplication, so if I do that multiplication, I get 100t minus 50. And that's the equation we had already got here and here and in the original question. Boy, there's a lot more to math than you think, right? Anyway, thanks for paying attention, and I'll revisit this in grade 11.